This is a solution that is increasingly applied. Insurance companies are extremely interested in climate change adaptation, and they hire people, experts in statistical analysis, in probability, in decision theory, because they want to know the risk. They want precisely to estimate the risk they run for when they activate insurance programs. So this is a possibility, but also early warning system. If we were able to forecast a drought with a couple of months in advance, there are a lot of things that we could, a lot of mitigation solution, mitigation of the impact that we could activate. For instance, we may accelerate the growing process of the production. We can take the fruits in advance, and we can take the production in advance, and we can activate water storage, or we can save water in reservoirs. So can you imagine if I was able to predict now that in June, so in 2 months from now, there will be a significant drought. I can increase the storage in reservoirs. I can start saving water now. I can start water saving programs now in order to keep the water in the reservoirs. Actually, we can't now predict droughts with a couple of months in advance. There is a lot of research activity. Early warning with respect to floods. In irrigation systems, when they realize that a flood is coming, they close the canals. They don't want dirty water. They don't want flood water into the canals, because flood water is muddy, is provoking siltation, is reducing the efficiency of the canals. So, I mean, these solutions to reduce the impact of extremes, it's indeed interesting. It's an interesting solution. Now, let me conclude this lecture by anticipating something that we will discuss later on. When we will discuss decision theory, we will discuss the way to get the best decision. And we will discuss methods for reaching a compromise between people. And this is a huge topic nowadays, because today we are accepting the concept that decisions regarding sustainability, decisions regarding water resources, decisions regarding vital elements like water should be taken transparently and by involving stakeholders. I mean, in the past, it was not like that. In the past, the king decided, and what the king decided was done. And today, we are relying on the concept of involvement, of inclusivity of people in decisions. This is really an hard task. It is nice to say, we are taking a decision based on people, but it is really an hard task, because when you have to put together several different expectations, several different aspirations and wishes to reach a compromise, it is not easy. And this is why we use decision theory. And a fundamental pillar of this concept of inclusivity, transparency, is the bottom-up approach. What does it mean, bottom-up? It means that you start from people, you start from the grassroots. I mean, you start from the end users, and it is the end users that take the decision, who take the decision. It's not the king, it's not the top of the pyramid. And so bottom up means that you don't start from the top of the pyramid and you go down to people, but you start from people and go up to the top. And the decision is taken from the top, of course, because institutionally you need that decisions are taken by the institutions that are in charge of taking decisions, but they take a decision basing on the consensus that they got from people. This is really the concept of the bottom-up approach. And in terms of climate change, the bottom-up approach, or let me start from the top-down approach. In terms of climate change and climate change mitigation and adaptation, we mean with the top-down approach, the approach that starts from climate models, climate predictions, and then goes down to problems, solutions, and then benefit to people. This is the top-down. You start from, I think I already discussed this with you. You start from the model prediction. Bottom up means that you start from the current problems and from people. You listen to people, their problems, and then you identify solutions basing on the opinion of people. And then you may check with climate models if solutions are sustainable. I think I have a sketch here which refer to floods, you know, and you see future society, and the top down is you start from the future, and the future means a model, predicted climate and predicted river flow, predicted inundation, and failure probability. So it means that at the end of the story, you find you quantify the problem, and then you get to people. People benefit are the last ring of this chain. The bottom up starts from people, and then by listening to people, you identify the failure possibility, and then you go back to the runoff possible climate and possible society. So basically you find the solution first, and then you see if the solution is compatible with what we think will be the future climate and the future society. What is another advantage of this approach? Another advantage is that you are focusing on the current problems. So usually when we get concerned by climate change, by environmental change in general, we start from a problem. So usually there is a flood occurs, and then people say, okay, the problem is climate change. And then usually our concern is always motivated by an existing problem. So a flood occurs, people blame climate change, and then the top-down approach says, okay, let's predict the future climate, blah, 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 and then we get to the solutions. The bottom-up approach, basically, after the problem, identifies a possible solution to the problem. So we got the flood in the Romagna region in 2023. So let's identify solutions to avoid that if a similar event occurs tomorrow, we don't get flooded again, okay? And in the present situation, if the same event occurs in May 2024, we get flooded again, of course, because we didn't put in place any solution. So let's identify a solution to avoid that the current problem repeats. And then we have to listen to people, of course, because the solutions require, like detention basin, requires the occupation of some areas that have to be taken from the owners and converted to public areas and reserved for the detention basin. Okay, fine. This is quite sensitive, but if we start from people, we can solve it. And then once we have a solution to the current problem, we can use the models to check if the solution is resilient against what we think will be the future climate. So basically now we are trying to push this bottom-up approach, but starting from people is complicated. And starting from people, it means decision theory, because you have to explain to people that the solution that you think is the most appropriate, you have to explain to them why, in a convincing way, why this is the best solution, in a convincing way. It's not an easy task. It is also a matter of personal inclination, personal skill. There are some people that are really good in seeking compromise. By the way, this is one of the skills that are very much appreciated in the 21st century. ability to team working, ability to seek compromise between different opinions. This is also a personal skill, can be trained, but it can be, of course, supported by study, by education. But on the other hand, it's also a matter of something that is very personal that you have to really seek. And it is not easy. It is really not easy. Okay, and that's it for this lecture. So let me go out from the PowerPoint. Any question? We still have 15 minutes or so. No questions. Let me see the chat. No messages. Okay, good. I would say that now I talked a lot. It's time to look at an exercise before going to the next one. I will skip, I anticipate, I will skip climate change and water. And this is something that you can find in the left column of my website. And it is this lecture. I'm opening it. I think it is an easy and interesting reading. I suggest you, not for your exam, but for your personal education, to have a look at it. And I mean, it's a web page that is already a bit, I think it is 5 or 6 years old, but I'm keeping it updated. And by the way, if you look at the left column of my website, you find some links that you may find useful. And definitely, I think I already advertised this, but this ebook, A Travel Through Time to Explore Past and Future Mega Droughts, I think it is an interesting reading. The timetable of the exams, I see a message in chat. You look at you go on the website of our course, in my website, climate change adaptation, and then you click here and you find the timetable, okay? We discussed it already some time. Okay, so as I said, I will skip this lecture. And the next one will be inductive and deductive estimation of climate change and climate impact, how we can estimate climate change. Inductive means through data analysis, deductive means through models, but let's skip it for now. So, I mean, I will talk about this next Monday. And now, I think it could be a good way of using these 10 minutes that are left to introduce the next exercise, computation of risk associated to flood events. There is a suggested R code. I would like to dedicate some time to this exercise next Monday. Anyway, I suggest that you take a look at the material for this exercise before Monday so we can be more efficient. And in particular, let's click on this link and let's open it. And you see that there is a PDF file with the text. Let's open it. Computation of risk associated to a flood event. Okay, so let's read the text. Annual maximum peak flow in cubic meters per second. Remember, flow is defined as the volume of water per unit time that flows through a cross river section, and we defined the cross river section, I think, 1 or 2 lectures ago. Okay, so the unit of flow is volume divided by time, and usually for rivers is cubic meters per second. So these annual maximum peak flows were observed for a river along 150 years. This allows you to estimate the probability distribution of the annual maximum peak flow. So it's probability distribution of extreme peak flow, okay? We will see how. It is very easy now. And the data reported in the text file that is included in the zip that I just opened, okay? And these are 150 numbers because it's annual maximum peak flow. By the way, it is a usual procedure in hydrology to estimate the probability distribution of peak flow by fitting data of annual maximum peak flow. This is a quite established procedure at the technical level. It is very easy. Okay. The river is protected by levees so that vulnerability is kept to zero up to a river flow of 12,000 cubic meters per second. Then vulnerability is increased linearly to 1 for a peak flow of 18,000. So let's see the vulnerability. It's this one. This is the vulnerability curve. Okay. So from 0 to 1 on the vertical axis, and this is the river flow. Once again, vulnerability 0 up to 12,000, and then there is a linear increase from 0 to 1 from 12,000 to 18,000. Okay, good. The exposure now of the flood-prone area is null up to a river flow of 8,000. We discussed the pattern of vulnerability and exposure a couple of lectures ago, and we said that up to a certain river flow, it's quite common to assume that you don't have any exposure, okay? And then exposures increase linearly up to a value of 12 million euros for a river flow of 16,000, and you see here the progress, okay? 12 millions is a reduced exposure. It must be a very small inundation, okay? Because you can understand, usually we talk about billions of damage after a flood, billions, not millions. Okay, now compute and plot in a graph the risk associated to flood events for peak flow ranging from 0 to 30,000. Compute the risk by the relationship risk is equivalent, is equal to probability times vulnerability times exposure, where probability hazard is computed with the log normal probability distribution. So it's, remember, it's a probability of exceedance, okay, to be computed with the log normal probability distribution, and it's the logarithm of the normal. It means that you take the data, take the logarithm of the data, and you fit a normal distribution to it. Okay. For each peak flow, use the probability of not exceedance to estimate P. Okay, and make a reasoning on the meaning of the obtained risk values. What do they mean? So I didn't remember this. So let's use the probability of not exceedance to estimate P, okay? And make a reasoning on the meaning of the obtained risk values. What do they mean? Okay, now let's focus on the problem. It's a detail, the fact that we can use P in terms of not exceedance or exceedance. You remember that the probability of exceedance is the complement to 1 of the probability of not exceedance. So it doesn't change much. And what do they mean? If we use, let's discuss this later, okay? Okay, just as very brief introduction, let me open an R console here, okay, R, and I clear the screen. Log normal distribution. So if I generate data with the normal distribution, you remember how we can generate them. So normal data, we can generate through the function rnorm, and then it means random from the normal distribution. And then we, let's generate 1000, and let's give a mean value of 0, or let's say a mean value of 10, and a standard deviation of 1. Okay, this is normal data. If we make the plot of this data, normal data, type equal line. This is the resulting plot. 1 second, I show it to you. This is the plot, okay? And let's put it here. Let me reduce it. Okay, good. And if I plot the density, plot density of normal data, yeah, type equal line. What are you expecting? I am expecting a bell. Let's see. Here it is, the bell. It's the probability density of the normal distribution. Good. We know this because we studied the normal distribution. Now, let's compute this. L normal data. Normal data is equal to exponential of normal data. Very good. So we got this plot L normal data. Let's look at the plot. You see that is much different. Okay. Let me just show you the plot of the normal data and the plot of the log normal data. So the log normal data look more like a river flow. If you plot the series of the Po River, you get something that is quite, I would say, more similar to what you see on the screen with respect to this one. Okay, and they are only positive. If I look at the density, plot density of log normal data, let's look at the density. You see that it is heavy-tailed. There is a long tail over the right. Again, it is a more reasonable solution for river flows because we said that river flows typically have a density that is not symmetric, as it is long-tailed with a long right tail. And so the log normal distribution is definitely more appropriate to fit the probability of river flows. This is why in the exercise it is suggested to use the log normal distribution. Good. And how can we determine the probability of log normal data? So we have here log normal data with the vector L normal data, okay? Normal data. So let's take the max, for instance, or yeah, the max. This is the max, and let's now compute the probability of this value. Okay, it can be computed with PL norm. Let's put this value 511782. Oops, 5782. Of course, I am expecting a probability of not exceedance that is close to 1. Okay, but besides telling R that I want the log normal distribution, I have to give the parameters of the log normal distribution. And I think that what we have to specify here is the mean. Let's see, if I put the mean of log normal data and the standard deviation of log normal data, let's see if I get a correct estimate of the probability, which should result close to 1. I don't remember whether I have to put mean standard deviation of the log normal data or their logarithm. Let's see. So, yeah, sorry, I made a mistake here. Let's see. Let's try with the mean of, yeah, this is definitely the right syntax, okay? So when you want to estimate the probability for the normal distribution, you have to give the number, probability of not exceedance, and I put the max, so I was expecting a probability of not exceedance close to 1, and then you have to put as parameters the mean of the logarithm of the data and the standard deviation of the logarithm of the data. Here, what I could do in order to be better understood, is this one, log, and again log. So mean and standard deviation of the log of the data. This is the way to compute the probability from the log normal distribution into R. Okay, I think I can stop here. Any question while I stop the recording?